decision made possible through technological advance. Assume standard model is correct. There are two tricky conjectures of fundamental importance. One, they must be dark matter. Second, tile dwarf galaxies form out of the collision debris of other galaxies. He was perhaps the first one to actually put up these conjectures, and both have to be true. So we have here the structure formation tree. Small dark matter halos form first. They accrete baryons, which make stars. The dark matter halos merge to make the current dark matter halos in which the galaxies are a small baryonic object. This is what a dark matter halo looks like. There's a negative image. Our Milky Way would be a small disk like that in here. This is the size of about 500 kiloparsecs, and there are these many substructures which are milling around in this object. So this has two immediate implications. There exist large numbers of dark matter-dominated satellite galaxies. There exist large numbers of newly formed tile dwarf satellite galaxies that do not contain dark matter. This is okay, but are there two different types of dwarf galaxies? Because we expect the one case, galaxies to form in dark matter halos, and in another case, galaxies to form without dark matter halos. Those are the tile dwarf galaxies. Here's what we know about stellar systems. Here's the size against luminosity, faint, bright. This is 1 million solar masses. Here are star clusters, and this is where what we call galaxies appear. Up here we have 10 to the 10 to 10 to 12 solar masses, so these are elliptical galaxies, and these are our objects of interest, the dwarf ellipticals and dwarf spheroidal satellites, and we see there's only one population of galaxy. We do not see a spreading or two populations. So the answer to this is no, there is only one type of dwarf galaxy, but which one? And why only one? Let's first look at the dark matter type satellite galaxy. This can be tested by looking at the mass luminosity relation, which Simon has already mentioned. So we have here the mass of the dark matter halo, and here the luminosity of the object. What we expect is that the more massive satellites would be brighter. Larger bucket holds more water. That's essentially the physics behind it. And so we expect a positive slope. So there's a log mass versus log luminosity relation, which can be specified by the slope. And this is what the theoretical models show. You can see here there is indeed a slope. The more massive satellites in the theoretical lambda CDM models are brighter, which means that the dark matter models are okay and they are internally consistent. And we've already seen that the observations show a very different picture. This is what we expect, and that's what we see. Reality does not care about the dark matter in these systems. Okay? Thus, the concept of dark matter halos appears to be unphysical for those spheroidal satellites. Dark matter halos, I think, are ruled out. But that's only one argument. We could always say there's an error in the argument. Let's look at morphology. Here the idea is that we observe that the stars move with 7 kilometers per second in these objects, which means that in a few 100 million years they cover the size of the object. And so any substructure in the satellite should phase mix away if this velocity dispersion is really due to a dark matter halo. So however, we see significant isotopic distortion in many of the dwarf spheroidals. Is this consistent with dark matter? Well, here are some examples. This is Ursa Minor at a distance of 65 kiloparsecs. It has about 500 parsec size. And this S shape and general morphology is simply not really consistent with it being in this 10 to the 9 solar mass dark matter halo. What you have to realize is that this thing is in a dark matter halo which is vastly larger than this satellite. Here's another case, Fornax, at a much larger distance, and you can see how distorted and off-center the isophotes are. And this is again not consistent with being embedded, shielded by an extensive dark matter subhalo, unless it was very recently hit by something. And there are many other cases. So the distortions apparent in many of the dwarf spheroidal satellites do not support the notion that they are shielded by these large dark matter halos. So dark matter halos are ruled out. That's another argument. The spatial distribution of Milky Way satellites is another way of looking at the satellite population. Gives us further clues. This is what it should look like. Our Milky Way is a little disk in here, surrounded by all the substructure. The substructure is essentially nearly isotropic around this system. It is not anisotropic. This is what our Milky Way looks like. So we have here the Milky Way disk, and these are satellites. These are the classical bright satellites, and these here are found by robots. A very different discovery history to these satellites, a different type of population, if you like, in terms of how they were discovered. This is going from, so this is the whole visual radius of the Milky Way. And if you turn this by 90 degrees, you see that they are highly anisotropically distributed. So is this a structure which actually is a rotational object? For example, a disk which is rotating like this. Now, what we can do is fit a plane to this and get a normal. The normal is defined by the outer satellites. However, the angular motions of these satellites are given by the inner ones because that's where we can measure the motions. These are too far away to measure the motions. And we find, so this is now the galactic sky, and these are the directions of the orbital angular momenta of these satellites, and they cluster, as you can see, with an uncertainty around here. Now, this is the normal of the bright satellites, and this is the normal of the independently discovered faint satellites. The fact that these are so close together shows that there's a correlated phase space population which is inconsistent with the satellites being dark matter subhalos that fell into the Milky Way halo in a group or individually. You can't get that sort of structure if you assume that they fall in individually. So the dark matter halos, I think, are ruled out. So within about 2 megaparsecs of the local group, we should not actually get the local group because having a local group is extremely unlikely. The argument there is you have 2 massive dark matter halos in the local group, Milky Way Andromeda, similar mass, and the probability that they are occupied by similar Milky Way, similar disk galaxies with similar satellite populations is known today from the lambda CDM simulations to be very unlikely. Okay, so these are just some numbers. And within 8 megaparsecs, that's a local volume. Again, so the likelihood of having the 3 massive galaxies above the local sheet is very small. And there are far too few galaxies in the void. And again, this likelihood of having that in a lambda CDM universe is very small. Furthermore, disk galaxy is far too similar. This is the invariant disk galaxy. You take one disk galaxy, you can actually compute what another one will look like. This is not possible under CDM because the galaxies have very different merging histories. They live in very different environments. The angular momentum in the galaxy should be different. 30 to 60% disk galaxies are bulgeless. There's no evidence for merger built-up bulges in a large fraction of the disk galaxies. Again, this is a very major problem for lambda CDM. So, do we live in a bubble of extreme exception? I think this is not the case. I call this the BEE hypothesis to save the concordance cosmological model hypothesis. And I think that is not the way to go. The dark matter ansatz fails. So let's now look at the alternative. Let's consider now the tidal dwarf galaxies. Zwicky's second conjecture. Tidal dwarf galaxies form when disk galaxies interact. These are disk galaxies with gas. You can see that as they collide, matter is thrown out, and you can see these objects which form. And these are the tidal dwarf galaxies. They are small dwarf galaxies. This is observed to occur. And here is another image. We have star formation in galaxy-sized clumps between the galaxies. So by direct observation, we see that new dwarf galaxies form, and they are baryon-dominated. We know that they can't capture the dark matter if it is there. So evolution of these tidal dwarf galaxies, are they stable? Do they survive? Take one of these, put them into a computer and evolve their evolution as they orbit for many billion years around a major galaxy. And this is what you get. The remnants, these are 2 snapshots on different orbits, the remnants have highly anisotropic phase-space distribution functions. They have baryonic masses of 10 to the 5 solar masses, few hundred parsec size, and large mass-to-light ratio, although they do not contain dark matter. Let's look at Hercules at 130 kiloparsec. You can see how squashed it is. And you see the size. It's about 180 parsec radius. This is an object which was calculated in 1997, and these parameters are amazingly similar to Hercules, with a large mass-to-light ratio, but no dark matter. And this is a real prediction 10 years before the discovery of this type of celestial object. Now today we know that the early star formation and chemical enrichment evolution is similar to the observed dwarf spheroidal satellites of these tile dwarf galaxies. Today we know that later dynamical evolution does not destroy the satellites. We know today that the number of old tile dwarf galaxies amounts to the DE population observed. We also know that the DE galaxies are observed to contain no dark matter, consistent with them being tile dwarf galaxies. Young tile dwarf galaxies have rotation curves showing the missing mass syndrome, but they cannot have dark matter. This may be a real evidence, real measurements of the breakdown of Newtonian gravity, and might be a real falsification of our LAM-CDM, but we only have 3 of such galaxies observed. Clearly we need more of them. So what about the disk-like configuration? Remember the anisotropic distribution of the satellite galaxies? And there's a relation between the bulge luminosity and the satellites. So this is easily understandable. Well, this is actually what we observe. So Andromeda has a more massive bulge than Milky Way, and it has more satellites. And this correlation is stressed first by Karachentsev et al. Using local volume galaxies. Both the disk of satellites and bulge satellite correlation are easily understandable in this scenario because phase space correlated satellites form naturally in the same event as the bulge does. You don't have to invent any new physics to get this sort of correlation. The mass luminosity non-correlation, well, there's no dark matter, so we don't have to worry about the amount of dark matter in these objects. And tile dwarf galaxies are known to form. They are the result of well-understood standard physical processes. Thus, a fully self-consistent tile dwarf galaxy scenario emerges, which very naturally accounts for the properties of these DE galaxies and dwarf spheroidal satellites. There's no consistent, in fact, a contradictory picture within the dark matter framework. There is simply no evidence for the existence of dark matter satellites, unfortunately. I think the theory is very beautiful, but it just has a problem. It doesn't work. Every prediction of the standard cosmological model failed. In fact, some failures can be resolved by introducing unknown physics. But on galaxy scales and beyond, failure remains the rule. There's this disk-halo conspiracy, invariant disk galaxies, preponderance of disk galaxies without bulges, likely to having a local group being essentially negligible. And you can make a list where standard model fails. Mons, in this case Mons, does well, but not always. We don't know because we simply don't have the resources to look at every single possibility. And remember this slide? Well, I think this is the correctest description of the situation. Standard model out, alternative in. So conclusions with some history. We had this slide with the geocentric worldview. It's exactly the same slide, just with a few words changed. The LCDM model based on Einstein. Make it fit by inventing inflation, dark matter, dark force. It's an alternative, more not accepted, is deemed to be more complex and unsatisfying, more needs dark matter, does not fit the data well, is claimed. Decision by technological advance, local group telescope data disprove the standard model, but are consistent with non-Einsteinian Newtonian dynamics. Conclusions, it is irrelevant to debate whether the LCDM model fits any data. The relevant issue now is what are Mond or Mach, etc., telling us about space-time inertial mass. And I think this is actually where one is seeing new physics, which is worthy of exploration. I'm not saying you should stop everything on lambda CDM, but that alternative is very important. And it's a pleasure to introduce these 3 people, Sanders, Hensel, and Shanks, who've come here on my invitation to be part of the debate, because I can't obviously answer all questions since I'm not fundamentally a cosmologist. So there are expertises here which would be useful. And I want to leave you, I'm finishing now with this new structure formation picture, which is based only on baryonic galaxies, where galaxies collide, and when they collide, which is then not so often, they spawn these new galaxies. So today you see the Milky Way plus its satellite galaxies. And that would be all. Thank you.